On the night of May 7, 2025, a Dassault Rafale, tail number BS-001, the very first Rafale delivered to the Indian Air Force, was blown out of the sky over Punjab. Its wreckage was found in a village called Akalia Kalan in Bathinda, approximately 70 kilometers from the Pakistan border. The killer was not a fifth-generation stealth fighter. It was not an American F-35 or a Russian Su-57. It was a Chinese-built single-engine export fighter that most Western defense analysts had dismissed as a budget alternative, a poor man's F-16. The Chengdu J-10CE had just achieved the first confirmed air-to-air combat victory in its history. The PL-15 missile that struck the Rafale had been fired from approximately 200 kilometers away, one of the longest-range air-to-air kills ever recorded. And by the time the wreckage was identified, the global arms market, the balance of power in South Asia, and the mythology of Western air superiority had all been permanently altered. This is the story of how it happened and what it means. 2 weeks earlier, on April 22, 2025, gunmen had opened fire on tourists near Pahalgam in Indian-administered Kashmir, killing 26 civilians, almost all of them Hindu pilgrims. The Resistance Front, a proxy of the Pakistan-based Lashkar-e-Taiba, initially claimed responsibility. India blamed Pakistan for harboring the perpetrators. Islamabad denied involvement and offered to cooperate with an international inquiry. But New Delhi was not interested in inquiries. It was preparing a military response. What followed was a rapid escalation. Diplomatic ties were downgraded.
Ow!
The Indus Water Treaty was suspended, visas were revoked, and borders sealed. On the evening of May 6th, the Indian military launched Operation Sindoor, a coordinated series of drone and missile strikes targeting 9 sites across Pakistan and Pakistan-administered Kashmir that India designated as terrorist infrastructure belonging to Lashkar-e-Taiba and Jaish-e-Mohammed. Pakistan called it an act of war. Its military vowed to respond at a time, place, and manner of its choosing. That response came just after midnight on May 7th, at Pakistan Air Force Headquarters. Air Chief Marshal Zahir Sidhu had been sleeping on a mattress just off the main operations room for days, anticipating exactly this moment. When the screens lit up with the positions of dozens of active Indian aircraft across the border, the scramble order was immediate. The Indian Air Force had launched a massive strike package, approximately 72 aircraft, including 14 Dassault Rafales, Su-30MKs MiG-29s, and Mirage 2000s. They were executing the second wave of Operation Sindoor, targeting what New Delhi described as military-adjacent infrastructure deep within Pakistani territory. To the Indian pilots, the Rafale was their premier asset, the machine marketed by France as the pinnacle of 4.5-generation technology. They sat in cockpits lined with glass touchscreens and holographic displays. Their SPECTRA electronic warfare suite, developed by Thales, was considered among the finest in the Western world. In joint exercises, the Rafale had performed impressively against F-16s, Eurofighters, and Su-30s. Indian defense procurement had positioned it as the guarantor of regional air superiority. According to Reuters, Air Chief Marshal Sidhu gave a specific instruction to his staff: target the Rafales. They were the jewel of India's fleet, and they had never been downed in battle. Taking one down would send a message that no amount of diplomatic language could match. The Pakistan Air Force scrambled 42 aircraft in response: JF-17 Thunders, F-16s, and critically, the J-10CEs of No. 15 Squadron. The Cobras, based at POF Base Minhas in Kamra, were the elite capital defense unit. They deployed 18 of their 20 J-10CEs for the intercept operation. Beneath their delta wings hung the weapon that would change everything: the PL-15E long-range air-to-air missile. What followed was what military analysts would later describe as the largest beyond-visual-range aerial engagement in decades, over 114 aircraft from both sides, fighting at standoff distances exceeding 100 kilometers. Neither side's fighters crossed the border. The entire battle, lasting approximately 52 minutes, was conducted through missiles, sensors, and data links. No pilot saw their adversary with the naked eye. And the Cobras did something the Indian pilots were not expecting. As they climbed into position, they did not activate their radars. They flew in total electronic silence, guided only by the encrypted data stream beaming down from a friendly AWACS, circling safely within their own territory. They were ghosts in the machine, sliding into position to execute an ambush that had been rehearsed in simulators for 3 years. Every vector, every timing window, every contingency had been wargamed. The Cobras knew exactly where the Indian formation would be. They knew its heading, its altitude, and its probable target set. They had been waiting. The Indian Rafale pilots, meanwhile, had a critical blind spot. According to both Indian and Pakistani officials interviewed by Reuters, Indian intelligence had assessed the effective range of the PL-15 at approximately 150 kilometers, the widely cited figure for the export variant. The Indian pilots believed they were operating outside Pakistani firing distance. To understand the destruction that followed, you have to look away from the fighters entirely. The J-10CEs were the executioners, but the architect of the ambush was orbiting hundreds of kilometers from the engagement zone, a slow-moving aircraft tracing patient circles deep within Pakistani airspace. This was the AWACS, the Airborne Warning and Control System. On that night, the eyes of the operation were likely provided by the SOB-2000. Erie or the Chinese-built ZDK-03 Karakoram Eagle, both platforms equipped with powerful dorsal radar arrays, capable of detecting aircraft at ranges exceeding 400 kilometers and looking down through terrain that would blind a fighter's nose-mounted radar. What made this engagement historically unique was its geometry. Neither side's fighters crossed the border. The Indian aircraft remained in Indian airspace. The Pakistani aircraft remained in Pakistani airspace. Entire battle was fought at standoff distances, missiles bridging the gap that the aircraft themselves never closed. This was not a dogfight. It was a network-enabled missile exchange conducted across more than 100 kilometers of empty sky. The AWACS gave the Pakistani side a lethal information asymmetry, the single most decisive factor of the entire engagement. The Indian pilots were navigating with their onboard sensors, nose-mounted RBE-2A, ESA radars, and passive electronic warning receivers. These systems are sophisticated, but they are constrained by physics. A fighter's radar can only see what is in front of it, and terrain masks what lies beyond the mountains. The Pakistani AWACS, looking down from altitude, suffered none of these limitations. It saw the entire tactical picture simultaneously: the vector, altitude, speed, and projected course of the Indian strike package. And critically, according to Pakistani officials, the AWACS fed this picture directly to the J-10Cs through encrypted high-bandwidth data links. The J-10Cs maintained total emission control (MCON). Their KLJ-7 AAESA radars remained dormant. To the sensors aboard the Indian aircraft, the airspace ahead registered as empty. No radar emissions, no electronic signatures, nothing to jam or track. But the J-10Cs were not flying blind. They saw the Indian formation painted on their digital displays, red icons moving closer, updated continuously by the orbiting surveillance platform. The pilots maneuvered into optimal intercept geometry without ever revealing their position electronically. This brings us to the tactical innovation that analysts believe sealed the engagement: network-centric off-board targeting. In previous generations of air combat, a fighter that wanted to engage an enemy had to illuminate the target with its own fire control radar, blasting the sky with high-energy radio waves. The moment a fighter activates its radar, it announces its position. The enemy's radar warning receiver registers the emission, and the element of surprise evaporates. On May 7th, the Cobras exploited a different architecture. The targeting data provided by the AWACS was reportedly precise enough to initialize the inertial guidance. Systems of the PL-15 missiles without the J-10CEs ever needing to activate their own radars. The weapons were released on a track file generated by the network. The J-10CEs did not need to expose themselves. They did not need to close to visual range. Did not need to engage in the spiraling high-G dogfights that dominate public imagination. They received coordinates, confirmed weapons parameters, and pressed the release. Then they turned away, never once exposing themselves to return fire. It was only after the missiles were already in flight, accelerating along their trajectories, that their onboard active radar seekers activated for terminal guidance. By that point, the Indian fighters were inside a closing no-escape zone they had not known existed. For the Indian pilots, the nightmare materialized seconds later, The missile approach warning systems screamed. By the time the onboard computers classified the inbound threats, the PL-15s were already in their terminal phase, active seekers locked, closing at hypersonic speeds. The Rafale pilots executed defensive maneuvers, dispensing flares and chaff, banking hard, pushing their throttles to the stops. They activated SPECTRA's active jamming modes, expecting the system to confuse or deflect the incoming seekers. The missiles did not deviate. This represented an evolution in Chinese-supplied military doctrine that Western analysts had underestimated: the ability to seamlessly fuse strategic surveillance data from an AWACS with the fire control systems of a tactical fighter requires robust, jam-resistant communication protocols, high-speed data processing, and extensive software integration. For years, Western intelligence assessments had assumed Chinese data link technology lagged behind NATO standards. The May 7th engagement demonstrated otherwise. The Rafale was not defeated by a superior dogfighter, it was defeated by a superior architecture. The J-10CE functioned as a networked launch platform, extending the reach of the AWACS into kinetic effect. The implications were immediate. In networked warfare, the side with the better information architecture holds a decisive advantage over the side with the better individual platform. The invisible net had held. Now came the killing blow. In modern air combat, the aircraft commands attention, but the missile delivers the verdict. The tactical architecture described above created the conditions for a kill. The instrument of that kill was a clash between two fundamentally different philosophies. Of long-range aerial destruction, the European Meteor and the Chinese PL-15E. The Meteor, carried by the Indian Rafales, is a genuine engineering achievement. It is one of the few air-to-air missiles in service that utilizes a solid-fuel ramjet engine rather than a conventional rocket motor. This air-breathing propulsion system allows the Meteor to throttle its speed, conserving fuel during the cruise phase and retaining energy for aggressive terminal maneuvering. The design intent is to maximize the no-escape zone, the volume of space within which no realistic evasive action by the target can prevent a kill. On paper, the Meteor's sustained energy across its flight envelope is superior to any traditional rocket-powered competitor. Indian Air Force planning had treated the Meteor as a decisive advantage. The assumption was straightforward. Even if the adversary fired first, the Meteor's superior kinematics would allow a retaliatory shot that could not be outrun. The PL-15E operates on a different principle entirely. Rather than breathing external air, it carries its own oxidizer and a dual-pulse solid rocket motor. This makes it independent of atmospheric conditions, a meaningful advantage in the thin air at high altitude where ramjet efficiency degrades. Here's where the intelligence failure proved fatal. Indian planners had assessed the PL-15E's effective range at approximately 150 kilometers, the widely cited figure for the standard export variant. Based on this assessment, Indian pilots believed they were operating outside the Pakistani engagement envelope. They calculated their safety margin accordingly. But according to Pakistani officials interviewed by Reuters, the PL-15 that struck the Rafale was fired from approximately 200 kilometers away. Indian officials suggested the actual range may have been even greater. If accurate, this represents one of the longest-range air-to-air strikes ever recorded. Some analysts have speculated that Pakistan may have received not the export variant but the domestic Chinese version of the PL-15, which has a declared range of 200 to 300 kilometers. Pakistani specialized publications reported that approximately 1 week before hostilities began, China allegedly supplied Pakistan with a batch of missiles directly from its own military stockpiles, weapons not subject to export restrictions. The range miscalculation transformed the entire tactical picture. The Indian pilots believed they were safe. They were not. When the Cobras received weapons release authorization, they were firing from a distance that Indian doctrine classified as beyond threat range. Upon release, the first pulse of the rocket motor ignited, accelerating the missiles upward along a lofted ballistic trajectory. They climbed rapidly into the stratosphere, altitudes where air resistance is negligible. In that near vacuum, the missiles converted altitude into velocity, cruising at hypersonic speeds with minimal drag. They became ballistic objects descending upon their targets from above. This lofting profile effectively extended the PL-15E's practical engagement range well beyond what the Rafale pilots had calculated as the threat boundary. The range gap, The difference between how far each side could effectively shoot became the defining variable of the engagement. As the Pakistani missiles tipped over into their terminal descent, the Rafale pilots detected the inbound threat. They were still outside effective meteor launch range against the retreating J-10CEs. To fire back with a reasonable probability of kill, they needed to close approximately 20 more kilometers, flying directly into the incoming missiles. Training and aggression drove them forward initially. They pressed the attack, attempting to reach their own weapons envelope. This decision proved catastrophic because they miscalculated the PL-15E's terminal behavior. As the Chinese missiles descended into denser atmosphere and closed on the Rafales, they did not arrive as decelerating, energy-depleted rounds. The onboard guidance computers, sensing proximity to the target, triggered the second pulse of the rocket motor. This is the defining feature of the PL-15E's lethality. At precisely the moment the missile should have been losing speed, it surged, accelerating from approximately Mach 3 to Mach 4.5 in seconds. For a pilot defending against an incoming missile, survival depends on draining the missile's energy, forcing it to turn, chase, and bleed speed until it can no longer maneuver. The PL-15E's second pulse destroyed that calculation entirely. It expanded the no-escape zone to engulf the Rafales at a moment when evasion was no longer geometrically possible. The Indian jets were trapped. They'd committed forward into a closing engagement and were now inside a kill volume they could not escape. The terminal guidance of the PL-15E compounded the problem. The missile is equipped with a miniature, active electronically scanned array seeker, effectively a scaled-down version of a fighter radar. This digital seeker is significantly more resistant to ground clutter than older mechanical scan seekers. As the Rafales broke formation and dove toward the terrain, attempting to mask themselves against the mountain backdrop, the AESA seekers distinguished the Doppler signature of the moving aircraft from the static returns of the rock and snow below. The Rafales deployed chaff clouds of metallic strips designed to create false radar returns. The PL-15E's seeker processing classified the chaff as stationary objects within milliseconds and maintained lock on the maneuvering targets. The defensive countermeasures that had been calibrated to defeat an earlier generation of missile seekers were insufficient against the digital processing of the Chinese weapon. The result was catastrophic. Rafale AWACS-01, the first of 36 Rafales delivered to the Indian Air Force, was struck and destroyed. Its wreckage was later found scattered across Akalia Kalan, a village in the Bathinda district of Punjab, approximately 70 kilometers from the India-Pakistan border. The aircraft had been returning to Ambala Air Force Station, home to a major wing of the IAF's Western Air Command, when it was hit, according to Pakistani claims. Additional Indian aircraft were also downed in the engagement. Pakistan asserted a total of 5 fighters, including up to 3 Rafales, AMI-G-29, and ASU-30MKI, along with one Israeli-made Heron UAV. India has never officially confirmed the specific number or types of aircraft lost, but the Indian Air Force acknowledged that losses are a part of combat while declining to provide details. In June, the Chief of Staff of the French Air and Space Force stated that he had seen evidence of 3 Indian aircraft being downed, including a Rafale and a Russian-made Sukhoi. Senior Dassault executives separately confirmed to French lawmakers that India had lost a Rafale in operations. The broader engagement, 52 minutes of BVR combat involving over 114 aircraft, resulted in no confirmed Pakistani aircraft losses. The J-10CEs returned to base intact. They had executed a standoff ambush and withdrawn before any effective counterattack was possible. The verdict was stark. It's a fighter that shot first, from beyond the enemy's assessed engagement range, won completely. The meteor never found its target. But the question that dominated the post-engagement analysis was not about the missile or the data link. It was about the shield. For a decade, the Rafale's SPECTRA suite had been marketed as a near-impenetrable defensive system capable of jamming, spoofing, and deceiving enemy radars with sufficient effectiveness to compensate for the Rafale's non-stealthy radar cross-section. SPECTRA was the reason India had chosen the Rafale over competitors. It was the system that was supposed to keep the pilots alive even in contested airspace. On May 7th, it was tested in combat for the first time. Understanding what happened requires examining both hardware and software and the intelligence assumptions underlying each. SPECTRA was designed in the late 1990s and progressively modernized through the 2000s and 2010s. Its threat library, the database of enemy radar signatures that tells the system what it is facing and how to counter it, was built primarily around Russian equipment. The radars of the Su-30, MiG-29, S-300, and S-400 systems. Against these threats, SPECTRA performs effectively. It recognizes the signal characteristics, identifies the operating mode, and deploys tailored jamming techniques, false targets, noise jamming, or deceptive angle manipulation. However, the J-10CE's KLJ-7A radar was not a Russian system. It was not derived from Russian technology. Developed by the Nanjing Research Institute of Electronics Technology, KLJ-7A is an indigenous Chinese AESA design, composed of over 1,000 individual transmissive modules, each capable of independent frequency and phase control. The operational difference is fundamental. A mechanical scan radar broadcasts on predictable frequencies with a rhythmic sweep pattern. An electronic warfare system like SPECTRA can learn that pattern, predict the next pulse, and inject a precisely timed jamming signal. It is a solvable problem. An AESA radar changes frequency thousands of times per second in a pseudo-random pattern known as frequency hopping. When the Rafales activated SPECTRA to jam the J-10Cs, the system detected a radar pulse on one frequency and generated a jamming response. But by the time that response was transmitted, the KLJ-7A had already shifted to a different frequency. SPECTRA was jamming empty spectrum, transmitting countermeasures against signals that no longer existed. The Chinese radar moved faster than the French countermeasure system could adapt. The J-10C maintained a stable weapons-grade track on the Rafales throughout the engagement despite active jamming. The KLJ-7A possessed an additional capability that compounded the problem. Focused beam burn through, because an AESA radar can electronically steer and concentrate the energy of all its transmit-receive modules into a single narrow beam. It can generate enormous power density on a specific point in space. When directed at a jammer, this concentrated energy overwhelms the jammer's ability to produce a signal strong enough to mask the true return. The radar signal simply overpowers the noise. The Rafale pilots were pumping maximum jamming power into the electromagnetic environment. The KLJ-7A responded by focusing a pencil-thin beam of radar energy directly through the jamming, achieving a signal-to-noise ratio that rendered the countermeasures irrelevant. The SPECTRA processors were saturated. The electronic shield did not degrade gradually. It collapsed. But the deeper failure was not in the hardware, it was in the intelligence. Electronic warfare effectiveness depends entirely on the threat library. If the system does not recognize the specific waveform, pulse characteristics, and operating modes of the enemy radar, it cannot deploy the correct countermeasure technique. Western intelligence agencies had invested billions cataloging Russian electronic signatures. They understood Russian radar architecture intimately. The KLJ-7A's waveforms, algorithms, and operating modes were a different electronic language entirely. The specific signatures of Chinese AESA radars were likely absent from or inadequately represented in SPECTRA's threat database. When the Rafale's sensors detected the J-10C's emissions, they encountered signals they could not properly classify and therefore could not effectively counter. This exposed a critical blind spot in Western defense planning: the assumption that Chinese military electronics were derivatives of Russian technology. For years, the analytical shorthand had been that jamming Russian equipment meant jamming Chinese equipment by extension. The Kashmir engagement demonstrated that the Chinese defense electronics industry had diverged significantly, developing indigenous architectures with distinct signatures that existing Western countermeasure libraries were not prepared to address. The KLJ-7A also employed low probability of intercept techniques, deliberately reducing its emission power and masking its signals within the ambient electromagnetic noise floor. These techniques were specifically designed to delay detection by Western-designed radar warning receivers, buying additional seconds of invisibility during the critical approach phase. The radar could search and track while emitting at power levels so low they blended into the background radiation of the electromagnetic environment. By the time the Rafale's receivers classified the emission as a genuine threat rather than noise, the tactical situation had already evolved past the point of effective response. This is the paradox that modern electronic warfare must confront. a system designed to counter powerful identifiable radar signals is inherently vulnerable to a radar that deliberately makes itself difficult to identify. SPECTRA was built to fight loud enemies. The KLJ-7A whispered, and when it finally shouted, it shouted with focused, overwhelming power that no defensive system in the Rafale's weight class could absorb. The failure also exposed an institutional blind spot in how Western nations approach electronic warfare updates. Threat libraries require constant refresh. They must be updated with new signatures as adversary systems evolve. But obtaining accurate electronic intelligence on Chinese AESA radars requires either signals intelligence collection against operational Chinese or Chinese export systems, or cooperative sharing from nations that operate them. Neither source was readily available to Indian Air Force planners in the quantities and quality needed to prepare SPECTRA for this specific threat. The result was a compound failure. The Rafale's pilots trusted instruments that showed no threat. The instruments were being defeated by a system they did not recognize. And the jamming capability they relied upon was insufficient against a radar that moved faster and hit harder than anything. Their threat library. The J-10CE had not merely outflown the Rafale, it had outcomputed it, and the implications extended far beyond the Himalayas. The ceasefire, brokered on May 10th after intense back-channel diplomacy with the United States, Pakistan and India, all claiming varying degrees of credit for the agreement, halted the fighting after 4 days. But the geopolitical aftershocks were only beginning. The claims, the wreckage, photographs, the electronic signatures, all of it circulated globally within hours. The confirmation, first by U.S. officials speaking to Reuters with high confidence that Pakistani J-10 aircraft had shot down at least 2 Indian fighters, then by France's air chief, who stated he had seen evidence of 3 Indian aircraft losses, including a Rafale, sent tremors through the international defense establishment. Senior Dassault executives separately confirmed to French lawmakers that India had lost a Rafale in operations. China's State Administration of Science, Technology and Industry for National Defense later named the J-10's first air-to-air combat victory as one of the 10 most important developments in China's defense industry for 2025. Dassault's aviation stock came under pressure. The exact market impact was debated, but the direction was clear. The Rafale's most powerful marketing asset, its unblemished combat record, had been lost. The Lee's manufacturer of the SPECTRA suite faced similar scrutiny. The premium pricing model of Western defense equipment rests on an implicit promise of technological superiority. That promise had been publicly challenged. The reaction in Beijing was measured and strategic. In July, Wang Gang, a senior Chinese defense official, visited Pakistan to discuss how Chinese systems established the kill chain that led to the Rafale shootdown, according to Pakistani Air Force officials. When asked about the meeting, Chinese authorities did not comment. But Pakistan's military stated that Wang had shown strong interest in PAF's operational experience in multi-domain operations. The Chengdu Aerospace Corporation did not need advertising campaigns. The combat footage was the most effective sales tool in the history of the global arms trade. Within weeks, military attaches from dozens of nations were requesting technical briefings on the J-10CE. The strategic impact on the global arms market was potentially more significant than the tactical outcome itself. For decades, the international fighter market has operated on a tiered system. At the top, American fifth-generation platforms, restricted by Congress and available only to the closest allies. Below that, European 4.5-generation fighters Rafale, Eurofighter Typhoon, Gripen, marketed as the best available alternative. Below that, Russian and Chinese platforms sold primarily to nations that could not access or afford Western equipment. The Kashmir engagement disrupted this hierarchy. The J-10CE, priced at roughly $40 million per unit, less than half the Rafale's cost, had demonstrated the ability to engage and destroy a top-tier Western fighter in realistic combat conditions. The performance gap that justified the price differential had narrowed dramatically. The mathematics were difficult to ignore. For the cost of a single squadron of 12 Rafales, a nation could field nearly 3 squadrons of J-10CEs, supported by AWACS platforms and stocked with PL-15E missiles. In a prolonged conflict where attrition matters, numerical advantage compounds, military procurement officials from the Middle East, Southeast Asia, Africa, and South America Nations that had been weighing expensive Western options against more affordable Eastern alternatives now had combat data to factor into their calculations. The J-10CE had earned something that no amount of airshow demonstrations or glossy brochures could provide: a verified combat record against a peer-level adversary. This represented what defense economists call the triumph of the cost-exchange ratio. The philosophy that quality always defeats quantity assumes a significant capability gap between the expensive and the inexpensive platform. When that gap closes, when the budget fighter can effectively engage the premium fighter, the economic logic of the premium purchase erodes. The J-10CE did not need to be better than the Rafale in every parameter. It needed to be effective enough in sufficient numbers, at a sustainable cost. The Kashmir data suggested it had crossed that threshold. The implications cascaded through procurement offices worldwide. Nations that had committed to Western platforms faced uncomfortable questions from their own defense establishments. Nations that had been priced out of Western options now saw a viable alternative backed by combat results rather than marketing materials. The J-10CE had become the proof that air superiority could be democratized, that a second-tier power, properly equipped and properly networked, could challenge a first-tier adversary without bankrupting its treasury. This was not merely a commercial disruption. It was a strategic one. The post-Cold War arms trade had operated on an implicit hierarchy: American equipment at the top, European equipment as the accessible premium alternative, and Russian and Chinese equipment for everyone else. That hierarchy depended on a performance gap that justified the price gap. The Kashmir engagement narrowed the performance gap to a margin that the price gap could no longer justify, at least not without serious institutional reflection. The regional consequences were equally significant. Pakistan Air Force's performance restored a measure of strategic equilibrium to South Asia. The Indian acquisition of Rafales and S-400 missile systems had been intended to establish decisive conventional superiority. That calculus was now in question. New Delhi faced an urgent reassessment not only of specific platforms, but of the doctrinal assumptions underlying their force structure. The Indian Air Force operated a diverse fleet: Rafales, Su-30MK as MiG-29s, Tejas, sourced from multiple nations with different data architectures, different communication standards, and different maintenance ecosystems. The May 7th engagement raised a pointed question: was this diversity a strength or a vulnerability? Could these disparate systems be integrated into the kind of seamless network that had just destroyed two of their most expensive aircraft? The answer, painfully, was not yet clear. For Islamabad, the engagement validated both a procurement strategy and an alliance. The partnership with Beijing Chinese aircraft, Chinese missiles, Chinese data link architecture had produced a combat-proven integrated weapons system. The Iron Brother relationship between Pakistan and China had delivered a tangible strategic dividend. But perhaps the most consequential lesson was doctrinal rather than commercial. The engagement demonstrated that in 21st century air combat, the decisive advantage belongs not to the platform with the best airframe, the tightest turn radius, or the most expensive avionics. It belongs to the side that constructs the superior information architecture, the network that connects sensor to shooter to weapon with speed, precision, and resilience. The J-10CE was the visible element. The invisible element, the AWACS, the data link, the integrated fire control, was the actual weapon system. The Rafale, operating as a comparatively isolated platform, relying primarily on its own sensors and defensive systems, was outmatched by the architecture it was facing, not merely by the aircraft. This distinction matters because it applies universally. Every air force operating expensive Western platforms under the assumption that individual aircraft superiority guarantees dominance must now account for the possibility that a networked, mass-produced adversary can neutralize that advantage through superior integration. The events of May 7, 2025 represent not merely an incident, but a turning point. They illustrate a structural shift in the character of aerial warfare that had been theorized for years, but had never been demonstrated in combat between peer-level systems equipped with modern beyond visual range weapons. The Chengdu J-10CE, the vigorous dragon, was born from necessity. It was designed to defend Chinese airspace affordably and in numbers. Its evolution into an export platform capable of challenging the established order of Western air superiority reflects a broader transformation. The maturation of China's defense industrial base from imitation to innovation, the Rafale remains a formidable aircraft. Its aerodynamic performance, its sensor fusion, and its weapon options are genuine strengths. Dassault's CEO maintained publicly that it is the best multi-role fighter in the world, but the May 7th engagement exposed a vulnerability that transcends any single platform. The danger of underestimating a competitor's weapons range, the cost of operating without accurate threat intelligence, and the assumption that Western tactical doctrine would remain effective against a rapidly advancing adversary. The Dragon did not win because it was individually superior. It won because it was part of a system, networked, informed, and positioned to strike before the adversary understood the threat. It won because the intelligence picture that Indian planners operated from was fatally incomplete. And it won because it represented a cost model that an increasing number of nations can sustain. The lessons extend beyond any single airframe or missile. They speak to the nature of modern military competition itself. The advantage in 21st century warfare does not belong permanently to the nation that spends the most or fields the most sophisticated individual platform. It belongs to the nation or the coalition that integrates most effectively, that connects sensor to shooter to weapon faster than the adversary can react, that updates its threat libraries and electronic countermeasures against the actual systems it will face, not the systems it assumed it would face. The era of uncontested Western aerial dominance was already eroding. The May 7th engagement marks the moment the world was forced to acknowledge it. The J-10CE is no longer a budget fighter. It is a strategic instrument. It is a proof of concept for networked, affordable, lethal air power. And it is a warning to every defense planner, every procurement officer, and every pilot who has placed their faith in the assumption that the most expensive machine always wins. The Dragon is awake. Its claws are sharp, its reach is long, and its price is one that the world can afford. The question is no longer whether Chinese air combat technology works. The question is, who adapts first?